Dear members, it is our pleasure to have Professor Dr. Indranil SenGupta from Florida International University with us for this International Research Convention 2024 as a keynote speaker. It is my honor to introduce Dr. Indranil SenGupta. Dr. SenGupta received his PhD in mathematics from Texas A&M University in 2010. He is currently a professor in the Department of Mathematics and Statistics at Florida International University. His research interest includes mathematical finance, stochastic processes, and data science. He has published more than 50 papers and book chapters in various high quality peer reviewed journals. His work appeared in notable journals such as SIAM, Journal of Finance Mathematics, Annals of Finance, Applied Mathematical Finance, etc. He has been invited to present his research in more than 70 national and international conferences, seminars, and colloquiums. So far, he has been the research advisor for the seven PhD students. He is the winner of several teaching and the service awards. He has served in the editorial board of various journals. On the behalf of Directorate of Research and Publication and the convener IRC 2024, we extend a warm welcome to you, sir, to this international research convention. Mike is over to you, sir.
Okay, yeah, thank you very much. May I share my screen at some point of time?
Yeah, yes.
Because I cannot see how to share. But, I think somebody should give me a sharing option.
Sure, sure. Pankaj, sir? Just a minute, sir. Just a minute, Professor.
Sure. Okay, now I think I can. Can you see my screen?
Yes, please.
Oh, you can see the screen, right?
Yes, absolutely.
Okay,
It's
okay.
fine.
So then
It's
I can
fine.
get started. Okay. So
Yeah.
thank you very much, Dr. Gupta, for the introduction, and I would like to thank my friend Dean Chakraborty, Prashan Chakraborty, for inviting me for presenting in this nice occasion. So by training, I'm a mathematician, so my talk will be a little bit mathematical. So what I'm going to present is an optimal portfolio analysis and machine learning. So this is basically a connection of financial mathematics and data science, and how we can use this in practical problems like portfolio management. Okay, so I'll get started. So my talk actually has three parts. One is the financial models in risk management. The second part is I'll be showing some refinement of financial models with data science-based techniques, in this case, machine learning and deep learning. And finally, a very short presentation on how we can use this for portfolio optimization. Now let's get started with the first part, financial models in risk management. As we know that financial assets or financial time series, for that matter of fact, for different assets, they share many common features. For example, they have heavy tail distribution of log returns. They have aggregational Gaussianity. They have quasi long range dependence, just to name a few. There are many other features which are common for all the financial time series data. And there are some other features which are not so common for other like financial time series data. So they're both. And hence, we need to have some sort of modeling. And now, here is a caution regarding modeling. All financial modeling is actually a trade-off between realism and tractability. So that's a very well-known fact that we can create beautiful models which are mathematically very tractable, but which may not be capturing the reality. On the other hand, if you want to capture reality in toto, maybe it's analytically impossible to track. So it's always a trade-off between the how much tractable or mathematically tractable we want the model to be versus how much it's real, in the sense that how much the reality is capturing. Okay. So, so key to a particular model is the actually the nice balance between this realism and practical. And now this is a well-studied section in financial math, like this kind of modeling, and it turns out that I'll have to be a little bit technical, because this are successfully captured by some stochastic processes, which are called to be the Levy processes. And Levy process is a very big thing in financial mathematics nowadays. I'll be briefly mentioning it. So this is sort of the building block of modern day financial mathematics. Okay. Now, so since, well, again, this slide is a little mathematical, but don't worry too much about it. I'm just introducing the Levy process here. So this is so-called Cadillac. Don't worry too much if you are not mathematician. It's a Cadillac stochastic process, which has basic three properties. One has independent increment, one has stationary increment, and one is stochastic continuity, meaning that whatever is happening in one interval is pretty much independent with whatever is happening on other disjoint intervals. That's the independent increment. And stationary increment means if we are waiting from between time 0 and 10 seconds, and 10 seconds and 20 seconds, those two increments are actually following the same distribution. That's the stationary increment. And almost surely these processes are like, so stochastic continuity is pretty much what is written here, the last one. Now, so this is what will be a good example. A good example would be a Brownian motion, for instance. But Brownian motion is just an example. In fact, Levy processes are more than that. For instance, in the market, when you see a particular financial market, the markets can have big jumps, big ups or downs. I don't know how many of you follow stocks, but if you follow the stock markets recently, in fact, just this week, like the week that ended yesterday, Tesla stock, for instance, had a huge drop. It sort of had a very big fluctuations. Now, those kind of fluctuations cannot be successfully captured by Brownian motion. For that, you need more than Brownian motion, which is Levy process. That includes the jump processes as well. Now, for the sake of the presentation, I'll describe a very particular model, which is called the Bernoulli-Nielsen-Shepard model. In short, this is called BNS model. This was introduced in various works of, and I listed some of the works here, various works of Bernoulli-Nielsen-Shepard in early 2001, 2002, the time frame around that. Okay. Now, one important thing is this kind of model is not only useful for financial purposes, but it has also independent interest in stationary time series analysis. For example, in the case of earthquake data analysis, this model are used. So I have known papers where this model is implemented for analysis, for estimating the earthquakes in some parts of Southern California. So here is the model. So this is so for this particular model, we consider a frictionless financial market. By frictionless, I mean it's a little unrealistic in the sense that we are not assuming any transaction cost. But at the same time, if you're if you're investing in any reasonable market, it's not really a big transaction cost. So I mean, we can approximate the market to frictionless financial market. And so what we assume is the stock price is given by this equation, the first equation. So it's ST is the stock price at time t. It's given by initial stock at 0 times e to the xt, where xt is the so-called Levy process that I mentioned before. So so xt is given by governed by this equation, where again, mu is a constant, this beta is a constant, and this sigma is the volatility of the Brown with corresponding to the Brownian motion. WT is the Brownian motion, and Z is the Levy subordinator, meaning that it has only positive increments. Okay? There is no negative jumps for this particular model. Okay? And also, the sigma t is also considered to be stochastic in the sense that it follows a OU type process, the last equation that gives you a mean reverting OU type process. So that's the utility of this sigma t function. So here sigma t is also stochastic. Okay. Now this model was again. I'll not go too much in details of this model, but this model was used in practice for various reasons. I'll show you a couple of examples. I mean, for those who took some courses in stochastic analysis, you know the last equation is very easy to solve, and if you solve it, you get something like this equation number 4. Now, what is so beautiful or so significant about this particular Barnoff-Nielsen-Shepard model? I'll just mention two brief advantages. This picture is from real market. So S&P 500 is it's observable in the market, and this VIX is the sort of proxy of the sigma t squared for S&P 500. So what I mean is, you can think of this like in the previous slide. When you have this ST can be thought of like in the real life or in the data set. ST can be thought of the S&P 500, and the sigma t in that case is also observable, and it's the VIX, and you can find both the data in the market. Now, if you look at the data, there are a very subtle feature. It is whenever the S&P 500 goes down, like here, I don't know if you can see my cursor, but if you see like here or here, when the S&P 500 market is crashing, or here, there is an immediate increase in the VIX price. Okay, that is a very well-known effect in the financial market, which is called the leverage effect. Now, for this particular model, leverage effect is sort of already incorporated because this rho is always taken to be negative. So if you see that when sigma is having a positive jump, then xt is having a negative jump. Remember, zt is the jump term, and correspondingly, st is having a negative jump. So that means whenever you have an upward tick in sigma t squared, there is a corresponding downward tick in st price, and that is a sort of already there in the model, and that's why this model is very interesting. And another thing for which this model is used in practice is, well, when you, as I said, when you solve for sigma t squared, this is the equation that you get. Now, if you look at the right-hand side, so all the terms are positive because zt is a subordinator which is only incorporating the positive jump, and hence this is positive, and everything is positive. So you can define anything you want, but the big question is when you're defining an equation like this one, when you solve it, will this sigma t squared be positive? That's a big question. For those who are familiar with the other models in the market, like Heston model, Harlan-White model, you know that it's not that obvious in that case. They have to use so-called Fomer condition to make it positive. But here it's sort of coming as a free. The right-hand side is always positive, so you don't have to impose anything on the parameters to make it positive. And you're very good. So if you just assume when you assume the dynamics of sigma t squared given by number 3. Okay. So I just gave you two brief advantages of this one, but there are many disadvantages also, and that's why we'll need machine learning. Okay. So here is some disadvantages. Now, again, empirical data that also shows that whenever there is a downward jump in the stock market, it does not really correspond to the immediate jump in the volatility market. Meaning, whenever there is a downward jump in ST, that does not mean there is an immediate upward jump in the sigma t squared. In fact, there is a lag period. So it can be typically the market may gather the information and take some time to react. Okay, so excuse me. So in that case, that is not really captured by the previously shown Barnoff-Nielsen-Shepard model. And so what I proposed in one of my earlier papers, this is a pretty old paper, 2016. So this is what I proposed is to, instead of the same Z for both the stock and volatility, we can have a different Z tilde for the volatility. And in that paper, I showed somehow this improves the result. Okay, but there are many other problems which are still unsolved. For example, it's known that the Financial Times series data has, to some extent, long-range dependence. To some extent, it's not really like very long-range dependence, but it's some extent it's long-range dependent. But the BNS model, it's known to be notorious for incorporating long-range dependence. Okay, in fact, the BNS model is a model that I showed just now. The BNS model, it fails significantly in the case of capturing the long-range dependence. And this is a picture from the real market. So if you see that an example of long-range dependence, this I took it from some oil market. So you see this x-axis on days. So this 50, 100 the days, and this is the correlation coefficient. So you see even after 100 days, the correlation is 0.8. So that is pretty big correlation. So that means we need some model that somehow incorporates the long range dependence. Okay, so if you have something which is definitely not long range dependence, that's no good. And hence, we need a scope of improvement of the Barnard-Nielsen and Shepard model. Okay? And hence come machine learning. So for various so what I'm going to show next is for various derivative and commodity price dynamics, the jump is not completely stochastic. By jump, I mean those big fluctuations are not completely stochastic. On the contrary, we should be able to implement some deep learning or machine learning based algorithm to extract a deterministic component, which in effect will improve the model. I'll dedicate the next few slides in order to explain this part, because this is not really this is sort of the core of the talk for me today. Now, before going into details, let me just mention that there are many techniques for doing this. In fact, I have been working in this area for last 5 or 6 years, and I wrote several papers with my PhD students. For example, these first 2 papers are based on sequential hypothesis testing methods in statistics for extracting those jumps using some sort of machine learning techniques. And here are the other papers. Here are 2 papers which I also wrote with a couple of my PhD students. These are also extracting the jumper based on some other techniques. So, but these papers are very like a mathematical. So I'll probably not go into that. Instead, what I plan to do, I'll plan to just discuss this paper, which was probably the first paper that we wrote regarding this area. Meaning how to sort of use machine learning to capture the jumps of the stochastic market, financial market, and then feed it back in the market to get a better result. Okay. Now, what we propose is something very simple. This is something which is very close to the Barnard-Nielsen-Shepard model. So if you recall, the Barnard-Nielsen-Shepard model had almost this times. dxt was something like this one, and then this one, and then there was a final term. And so what was absent in the BNS model was this 1 minus theta or this term. So what we propose is, instead of a single z, suppose we use 2 different z's. One is the z, and one is the zb. This zb stands for jumps. Okay, so it's a big jump. So b stands for big jump. And I'll explain what it means. So, and similarly, we do the analysis for the volatility model. Now, I would like you to focus on only the first part. Okay, so the idea would be, can we? So we have a huge source of data. So, so can we use the data to sort of predict or estimate this theta? Or suppose from the data you see that there is a premonition of a big upcoming fluctuation, then what would we do? We would simply just set this theta to be 1. That means this term dominates and this term just goes to 0, and then our model is something different compared to the old model. So now it's driven by zb instead of just original z. Versus analyzing the data, if you see there is no big upcoming fluctuation coming, you can simply set theta to be 0. And that's it. So that means the model is governed by the old Barnard-Nielsen-Shepard model. Okay, this is a very minor change, but that significantly changes the autocorrelation function in the next slide. So again, don't worry too much about this one. So all it means is the autocorrelation function, this is improved for this particular model. So this is sort of the mathematical result which shows the autocorrelation function in this case improves. Okay, so now I'll just focus on the data. Okay, and I'll show you a very concrete example. So this is actually you can find it this is a free data in the market. So we consider the crude oil price over the period of 10 years. And for this matter, we are using the West Texas intermediate data. So this is a visual of the particular set of data. So you see that this has, and this is actually taken from June 1, 2009 through May 30, 2019. So it's about 10-year data. I think it's echoing a little bit. Okay, so here I'm describing an algorithm. So again, what is the purpose? The purpose of this entire algorithm is to find the value of theta that I showed in the previous slides. Okay, so if I can find a good theta, then the model improves. That's the idea. And so this entire algorithm is dedicated to find the value of theta. Okay. So first step is, as usual, we'll conduct an exploratory data analysis. So like we do for any data set. Then what we do is we consider the daily close price for the historical oil price data. Okay. Now, and from the plots, we identify the value K, which we call a big jump. An example of this one would be, so suppose the oil price today, just an example, is 10, and tomorrow it becomes 5. Okay, so that means there is a jump of 5 units. Now, whether or not we call this 5-unit jump a big jump, that's up to you. That's up to whoever is modeling. So whoever is modeling this thing, so he or she would be taking care of the value of K, and that's why this is kind of subjective. And that's why I put it in red, that this K can be modified. Whatever you call as a big jump, that can be modified. Okay, so suppose you're modeling something with 10 units as big jump, and suppose other person is modeling with 20 units as big jump. Both can be true depending on the data set, but we have to be just careful. Now, step 3 is we create a new data frame from the old one where the feature. So now remember, for the original data set, we had just the dates and the close prices of the oils. And now we are creating a new data frame where now we have, say, 7 consecutive dates of stock or the oil price as a feature. And there, so that is the new data frame that we are creating. Okay. And this number 7 is also pretty ad hoc. You can change this number 7 to something else. And in fact, we have done this in our works. But here, just to be concrete, I'm showing you an example of this, this with this number 7. Okay. Now, we create a new target column where the theta is 1, provided for the next 7 days, you have at least 2 or more days of big jumps. Okay, so now we have said, so you can think this as the following way. You can see the data for 14 days. For the first 7 days, that's in the feature variables. For the next 7 days, you can see the data. And if you have 2 or more days of jump size, maybe 10 or more, you just put this data to be 1. If not, then put it to be 0. Now, why at least 2 jumps? That's also very ad hoc. You can change this to 3 jumps, 4 jumps, or whatever you want, depending on the data set. Maybe even 1 jump for some cases. And now you have a classic setting for the classification problem. So you have a feature variables, and you have theta equals to 1 and theta equals to 0. So you can run whatever we know, all those classification algorithms in machine learning for finding the value of theta, so 0 or 1. So, and in fact, in our, like in the slides that I'm going to show, we used 5 different methods. One is the logistic regression, one is random forest. Now here, for the neural network, we used a very, like, it's almost a shallow network. It's not even like it's deep network because it has 2 layers, but we didn't use much variables, like much nodes or much hidden layers. Just 2 hidden layers and very few nodes. Okay. Now the point is, I'll be showing you that even with this very simple case, we can sort of capture the value of theta pretty significantly. Now, we are not okay, but before doing that, let me just mention 2 other models that we used. So we also use the LSTM, which we'll call model B, and then model C is LSTM with the batch normalizer. These are pretty standard. Okay. Now, before showing the table, let me just mention one thing. So we are not claiming this is the best result in the universe. So what we are claiming is, even with this very simplistic model, we can capture theta value pretty good. And in our later paper, we actually improved this later results a lot, and we have much better results. But those are mathematically very involved. So here the main purpose is to show that even with this very simple neural network, we can capture the value of theta somehow. Okay, so here is tables for the here's a table for these five models. One LR is logistic regression, random forest, and then A is the neural network, B is the neural network, this is the LSTM, and C is the LSTM with batch normalizer. Okay? Now you see that for pretty much logistic regression is not capturing anything very well. For theta equals to 0, it captures something, but theta equals to 1, meaning that when you're trying to capture a big jump, it's failing miserably. Random forest, it's doing okay. But you see that, remember that A was the neural network with just 2 layers with very few number of nodes, and see the performance. And it's also improved in LSTM, and LSTM with batch normalizer, it's performing pretty well, even that very simplistic model. Okay. So that means that this method is actually working in a sense that we can use this for capturing the jumps of the market, and that was the entire idea of the paper. And once you find the value of theta, appropriate value of theta, you can always go back to the original model and improve it. And that's how typically these models, the stochastic models, are improved using machine learning algorithms. I'm almost out of time, so let me just quickly mention this portfolio optimization techniques. So now, what we do is for portfolio optimization is whatever I have discussed so far, we'll be using that model. And I'll show that we can construct reasonably a portfolio and we can sort of have some estimate on the or we can sort of have a control on the value function of that particular portfolio. So I have just a couple of slides left, so let me just quickly go over it. So this is a very well-known problem in financial market. The problem of portfolio optimization is of great importance for the financial industries. So this is what typically is done is that there is an utility function defined, which you call UT, and the goal is always to maximize this expectation, this conditional expectation. So UT is a utility function, and FT is the information up to that point, that particular time t. In our paper, which published 3 years back, so in SIAM, so we showed that this can be computed in a very nice way. So again, I'll not go over the results, but what I want to show you that is typically this is done by the so-called value function. So value function is the essential supremum of that thing which I just showed. And that can be obtained by the solution of a Hamilton-Jacobi-Bellman equation, which is something like this one. Again, these are just mathematical details. You don't need to worry about this one. What I'm going to show is the last result. So just I just want you to focus on this part, this equation in the middle. So it shows that J is a value function, meaning if you are given with a portfolio, J is a theoretical value of the optimal theoretical value of, so it is the value function. So that means if you in order to maximize the portfolio, so J, it plays a crucial role. Okay, but we have no control over it because that is something in the market, it's hidden in the market. I mean, there is no way you know this exactly. Okay? What we can know is this U tilde, so that we have control on. Now, so far, there are many researches which showed like there are constructions of U tilde, there are constructions of value functions. But the real question is how closely you are approximating the value function. And in our paper, we showed that for our 2 particular cases, we have actually an estimate of how closely we are approximating this particular value function using our techniques. So in other words, once we construct a portfolio, we can actually have hands-on experience with the value function, and we can tweak the value function in such a way that we can go until the optimal portfolio, or we can go until some extent to the optimal portfolio. Okay, so that is everything. Again, I rushed through this one, but everything on this one is based on the previous model that I showed. And so this is basically the improvement of the original stochastic model to the Barnard-Nielsen stochastic model to the Barnard-Nielsen stochastic model based on the machine learning, and then we implement it to the portfolio optimization to get this result. Okay? So thank you very much. Thank you for the opportunity for letting me talk in this session. Thank you.
Thank you, Professor. for this well-organized lecture and managing within the time frame. On the behalf of Directorate of Research and Publications, Sir Padampa Singhania University, and the convener IRC 2024, I'm sincerely grateful to you for giving us your this valuable time and managing and considering our request and managing it at such early morning. This was really exceptional contribution to the event. I'm sure your expertise and the insights will definitely enrich the experience of the attendees. Thank you so much, sir, for these valuable contributions. We are looking forward for such your contribution even in future as well. Thank you so much, sir. It is a pleasure to have you.
Yeah, thank you.